Physics describes the behavior of matter in space and time. When we get to learn physics at school, we get to know it as a discipline that describes the behavior of inanimate matter. It tells us how lights work, how atoms decay, or how rocks fall. We don't think of physics as a discipline that tells us a lot about ourselves, unless possibly that if you fall out of a window, you fall pretty much like a rock. But physics is so much more than this. Physics deals with the most fundamental laws of nature that describe the behavior of elementary particles that everything is made up, including us. And yes, that means that if we fall pretty much like rocks. But it also means that physics is the most powerful tool that we have to make sense of our own existence. It's a tool that allows us to answer questions like, how did we get here? What can we do? What can we know? What are we made of? And often it's given us surprising answers. For example, Einstein's theory of special relativity has taught us that the passage of time depends on how much you accelerate. Acceleration is a change of velocity, and velocity does have a direction. This means if you change direction, for example, by walking in a circle, you accelerate, and that slows the passage of time, which means if you run in a circle, you'll age slower. That's not a joke, it's actually true, and it's been measured, not for people who run in circles, but for airplanes that go around Earth. But it's an extremely tiny effect for the velocities that we can move with. So if you spend your whole life running in a circle, you might save a few nanoseconds, but maybe that's not how you want to spend your life. Einstein's theory of special relativity has taught us a lot of amazing things, but for me, one of the most surprising things is that it has told us that our perception of this present moment, of now, as something special is entirely subjective. It doesn't exist in the fundamental laws of nature. To understand why I say this, ask yourself whether I'm here now. Well, you might say, well, that's kind of a weird question that only physicists can ask. But the answer is not obviously yes. The reason is that Einstein's theory of special relativity is based on the observation that the speed of light is not infinite, it's finite, and it's the same for all observers, and nothing can go faster than light. So by the time you see me standing here, I've actually moved on into the future. You only see me as I was a little bit in the past. And yes, it's a really, really tiny delay, but you have this delay to everything you see around you. Everything you see it as it was a little bit in the past. And because no information can travel faster than the speed of light, there's no other way that you can find out what really happens now. So that's a little bit disturbing. You might say, well, but by the time that the light arrives at you, you could try to reconstruct, say, what you were doing when I was talking about rocks. You could say, well, at this time I was just scratching my head, because you know what the speed of light is, and you could measure the distance to me, and then you can figure out what happened simultaneously. The problem is that if somebody else does that, who's walking through the room, they get a different result, because some of the light would come at them and it would take a little less time to arrive at them, and some would come from behind, it would take a little bit longer. So they would reconstruct different things to happen at the same time. This is what's called the relativity of simultaneity. Different observers come to different conclusions about what happens at the same time. That's true when we're talking about the past, and it's also true when we're talking about the present. There is, in Einstein's theories, no way to reconstruct a moment of now that everyone agrees on. This notion of now that is so integral to our experience is entirely subjective. It depends on the observer. This also means that your now could be somebody else's past or somebody else's future. As a consequence, the past and the future in Einstein's theories exist exactly in the same way as the present moment. It's called the block universe because the block universe doesn't come into being, it just sits there like a block already in place. What does it mean? Well, I don't know, to be honest. It's one thing to understand what the mathematics says, and it's another thing entirely to interpret the mathematics. I think what it means is that we are beings inside of space and time. We don't see the full picture. We think from one moment to the next. We don't see how the universe has evolved and will continue to evolve. We don't see this entire big universe that we are part of. Physics has not only given us some surprising answers to questions that we might have asked, it's also a source of inspiration. Think about how often you encounter in movies or in science fiction literature concepts that have come out of physics. There's the multiverse, there are wormholes, time that slows down near black holes. It's all physics, really. It's just that the way that those topics are portrayed in movies or in the literature is, shall we say, a little bit more exciting than they appear in the scientific literature. Take, for example, the multiverse. That's the idea that there are other universes besides our own that we cannot observe and not interact with. The multiverse does appear in some of the mathematics that we encounter in the foundations of physics, but in those multiverses, you cannot travel between the universes. We're stuck in our own. Those other universes are completely disconnected from ours, so we can't observe them, we can't interact with them, and we also can't test that they are there. But mathematically, there are copies of our universe and of our planet with minute alterations, so each possible decision that you could have made was made by one of your copies in one of those other universes. Had chicken on the plane? Well, in some other universe, you had the noodles. In one of those universes, you won a Nobel Prize. In some other universe, you became prime minister. Maybe it's this one. So you could say, but wait, if we can't interact with those universes, if we can't observe them, if we can't measure them, then that's not scientific. And that's right. But just because it isn't scientific doesn't mean it's wrong. There's no observation that can refute or confirm the existence of those other universes, but we can't rule them out either. I like to call such ideas ascientific. That's a word which was coined by my friend Tim Palmer, and when he came up with this, I thought, that's brilliant. I'm totally going to steal this and now travel around and show off his word. I hope you'll forgive me. So the distinction between ascientific and unscientific is similar to the distinction between an atheist and an agnostic. The atheist doesn't believe in God. An agnostic has no opinion about it. In a similar sense, unscientific means you believe in something that conflicts with the scientific method. Could be, for example, that if you dance, that'll make it rain. You can test it, it doesn't work. Evidence speaks against it. An ascientific idea, to the contrary, doesn't have evidence that speaks neither for nor against it. For example, the existence of copies of you in those other universes. It's a science-compatible belief. Another example of such a science-compatible belief is that information is immortal in some sense. Now, information is one of those terrible words that is used in 50 different definitions over all fields of science. For our purposes, information is just all the data you need to specify a system at one particular time. It could be, for example, the solar system, where it would be the masses and initial positions and velocities of the planet. It could be all the data about the elementary particles that make up you. Now, it turns out that all the fundamental theories that we know work in a particular way, which is that you take the state of the system at one particular moment of time, then you have an equation that's also called an evolution law, and from that you can calculate what happens at any earlier, any later time. The interesting thing about those theories is that you can do this forward and backward. It's a one-to-one association. What this means is that the information in the state of a system, it's reconfigured, but it's never destroyed. We don't experience this in practice. If you say you burn a book for practical purposes, for your practical purposes, that destroys the information in the sense that it's no longer retrievable. But according to the mathematics of our theories, the information about the book that you burned is still there. It's contained in very tiny correlations between the atoms in the dust and the ashes and maybe the photons that came out. That's all fundamental laws we know, except for measurements in quantum mechanics and black hole evaporation, in which we don't really know what's going on. So to make a long story about this short, you can pick either belief you want, it's either destroyed or it's not destroyed, and physicists would buy it. So what this all means is that the information becomes irretrievable, but it can't be destroyed. It's something that we can't prove, but it's compatible with all that we currently know. Another big thought, so I was announced as the big thinking physicist, so I'm trying to do my best to live up to that expectation, is that the universe can think. And let me be honest, when I talked about this the first time, I think a lot of my colleagues thought, old Sabine has finally totally lost it. But look, I'm not saying that the universe does think. I'm saying everything that we currently know about the universe is compatible with the idea that it can think. If you look at the universe from far distance, then you'll see that the distribution of matter in the universe looks a little bit like the synapses and connections in the human brain. That's galaxies, galaxy filaments, and so on and so forth. And that's certainly suggestive, but there's a very simple argument for why the universe can't think, which is that it's simply too big. It takes a lot of time to send one single signal from one side of the universe to the other, and that's leaving aside that we don't observe any such signals. So even if the universe could think with all those synapses that would be the galaxies, it wouldn't be able to do a lot of thinking. That's the standard argument. That argument has a big gap, which is that it relies on Einstein's theory for gravity, which is general relativity. And that theory is not compatible with the theories that we have for matter, for the particles that live in that space-time, which all have quantum properties. That they have quantum properties means, among other things, that they can be in two places at the same time. We also know that those particles have masses, and masses generate a gravitational pull, which brings up the question, if you have a particle that's in two places at the same time, where does the gravitational pull go? Well, we don't know, because Einstein's theory of general relativity doesn't have quantum properties. So embarrassing as it sounds, we actually don't know what the gravitational field is of a single particle. What's all this mean? Well, it means that we need a new theory for the behavior of space and time and gravity. That theory, which we still don't have, is called quantum gravity. In this theory of quantum gravity, space and time can do wild things. It can, for example, be sprinkled with non-local connections that are kind of like teeny tiny wormholes that can connect one end of the universe with the other. And that can facilitate a lot of information exchange faster than the speed of light, instantaneously. It would give the universe a lot of connections through which it could interact with itself. Those tiny connections are too small for particles to go through. We know this because otherwise we'd already have noticed, but it does connect the universe with itself. Is that enough to allow the universe to think? Well, we don't know to begin with because we don't actually know what consciousness is, but it certainly gives the universe a lot more connections than even the human brain has. And this idea of those non-local connections has come up in various research topics in the foundations of physics. I myself haven't worked on it, I'm not that crazy. But I want to make this clear that I'm not saying that there's any evidence that this is actually the case. There's no evidence for those connections, and there's no evidence against them. It's compatible with all that we currently know that the universe can actually think. Don't worry if you didn't totally understand what I was talking about. I've been thinking about this for 20 years, and just among us, I don't totally understand it either. But I hope I've given you something to think about, and that I was able to explain what I mean when I talk about the other side of physics.